Hi, everyone. My name is Max. I'm an incoming assistant professor in the machine learning department and hopefully also courtesy and robotics. And I want to share a little bit about my research today. So I'm going to talk to you about developing generalist agents and a specific methodology towards generalist agents that starts with mathematical foundations and tries to move all the way to practical application. As a little bit of background, we're living in a really exciting time in the field of robotics, where we're seeing purpose-built robots being deployed for a range of applications, ranging from logistics to agriculture to food preparation. And if we think about all of these problem domains, as well as maybe even more ambitious ones, like having robots perform domestic labor or high-precision manufacturing, we ideally might envision a robotic agent that can perform all these tasks at a high-level generality, rather than having to develop a specific agent for the individual task at hand. But developing generalist agents is not simply a problem isolated to the domain of robotics, but in fact, and if we're going to move to general physical agents, we're going to need to make core advances in a range of machine learning disciplines to enable their generality. This isn't going to include processing things like video, having reasoning capabilities that rival those of LLMs, and potentially developing models of the world around us to predict the dynamics of our interactions with objects that we manipulate. The first step is to understand this problem from a mathematical perspective. So what we're able to prove is under certain conditions, we can bound the error that the robot makes at execution time by a measure of how well the robot fit its own training data, right? So this is preventing these execution time errors that we saw in the previous slide. Now, doing so with mathematical guarantees requires modifying the algorithm in a couple very substantial ways. The first is using ideas from classical control theory to correct for the small errors that accumulate over the course of a small trajectory. But it turns out that when the policy for the robot is a neural network, classical control theory is not enough because small perturbations to the robot's behavior, the neural network's input, will cause the neural network to respond in potentially highly unpredictable ways it's not described by a classical system. So instead, we have to add in some new techniques building on ideas from adversarial robustness to use training noise to give a certain inductive bias, which makes the robot more resilient to these small perturbations. And we introduce a new condition we call total variation continuity, which describes a specific kind of robustness that we might desire in learning how to imitate robotic trajectories. Now, what we're able to do with these two techniques is develop a theory that's incredibly general. In fact, we can show that arbitrary kinds of behaviors can be imitated this way, including ones that exhibit multiple strategies for solving the same task. So we call these multimodal or multiple modes in the data, for example, going left or right around an obstacle. And we're able to show that the robot can still learn to perform behaviors that exhibit this structure, even though these are not classically stabilizable by traditional control theory. The next step that we wanted to take is to understand what the diffusion models are doing on their own without algorithmic modification motivated by theory. So this is the scientific understanding phase. And again, we want to understand if diffusion models have some of these inductive biases when used as robotic policies that might lead to some native correction without us having to manufacture it with the other algorithmic tools. So in this forthcoming work, we study very closely the performance on diffusion models on a bunch of illustrative examples. This is the push-T environment from one of the original diffusion policy papers. And what you see visualized is the distribution of trajectories predicted by the diffusion model. And these distributions can be rather diverse in kind. And what we find is a couple of interesting things. So the first is we're able to show that this diffusion neural network, which is rather complicated, can be represented by a closed form simplification that admits analysis. Now, because the paper is not quite out yet, I won't tell you what that simplification is, but suffice it to say that it gives us a nice scientific model to understand what the neural network might be inclined to do in one way or another. In particular, we show that this simplification induces this property of total variation continuity that we saw in the last slide, the mathematical property that we want to encourage if we want robust policies to imitate a human behavior. And finally, we show that this property, this inductive bias, doesn't occur naively, but occurs in a certain transformation of the state space that the neural network learns, so that it's adapting it to the data at hand in a way that's rather clever and somewhat unexpected. I should also mention that there are a bunch of other interesting effects that show up with the interaction of behavior cloning and neural networks. In particular, how neural networks do their optimization drastically affects the performance of behavior cloning downstream. And some of these ideas ended up being very crucial to the training of large language models. And indeed, we've had transfer from ideas that we've seen starting with robotic behavior cloning and then using them for optimization paradigms in language as well. To conclude, I want to talk about developing new algorithms, right? So algorithms that we think are directly shippable to practical application. And this paper is about to be released. It's Diffusion Policy Optimization, where we present a specific way of using the classical policy gradient method in robot policies that are parameterized by diffusion models. And we find a couple of surprising things. The first that we find is that this technique drastically outperforms a bunch of other prior work using RL through diffusion policies. And the reason that it does this is actually motivated by things that we saw in the theoretical study, that using policy gradients can be thought of as performing these sort of low-level control tweaks to reject small errors. And indeed, our method excels at doing the fine adjustments that some of the other methods struggle with. We also find that this technique drastically outperforms reinforcement learning with other policy architectures as well. And we perform a very, very careful scientific investigation of why this diffusion policy optimization might be able to do better. And indeed, we find that it exhibits quite different inductive biases than we might typically see in traditional architectures. So for example, we're able to compare on some toy examples how our method does compared to a more standard approach for doing exploration reinforcement learning. And what we see is that the way that our method explores the data is a lot more structured around the expert demonstrations, rather than this kind of unstructured shotgun approach that sort of looks at things in a kind of less systematic way. And we find that this leads to improved sample complexity and exploration. The greater policy robustness also comes from some of these ideas of using training noise at training time that we observed in some of the theoretical work as well. And finally, I should mention the performance. We're able to show zero-shot transfer from simulation data to real-world hardware with our technique, whereas traditional policy architectures suffer quite considerably, even if we try to add additional techniques to make them more competitive. So this is an algorithm that we really do believe is going to play a big role at Toyota Research Institute, and we're attempting to scale it up in the months to come. To conclude, I wanted to discuss how this work on robotics influences and motivates my thinking about other problems in AI more generally. So robots need to predict their own actions. They might also want to predict what the world around them is going to do. And we've been thinking about how we might do sequence prediction or world model prediction in a more systematic way. So there's some wonderful work out with my collaborators on understanding how we can use diffusion as a unified approach to sequence prediction. And some of the ways we can get this to be a lot more stable than prior works build upon some of these ideas of robustifying behavior cloning that showed up in some of the theoretical work as well. And this method works for prediction video, predicting robot actions, a whole range of techniques. I should also mention that I'm actively working on decision-making in large language models, and we have some wonderful work with my very smart collaborators at Microsoft Research coming soon to understand some of the mathematical foundations and some of the key theoretical questions in this space as well. So just to conclude, if you're interested in this kind of work and you want to get in touch, you can find my website linked on the top left corner above. And just to reiterate, this work really focuses on understanding or moving towards agents in the physical world that can perform general tasks, as well as the various other AI advances that need to be concomitant with this in order to make this kind of vision come to fruition. And in particular, doing so in a way that incorporates mathematical foundations, careful scientific study, and tries to use these all to provide practical algorithms that are performant in practice. So if you're interested in this, please reach out, and I'd love to talk further. Thank you.